We are on page 20 in our notes today, and we're going to take a look at a special type of distribution called a normal distribution. So we've seen already how the mean and the median are related, how data can be spread from the mean and the median. Today, we're going to take a look at some special cases called normal distribution, where we get a pretty predictable pattern in the spread of our data. So normal distribution follows something called a normal curve. A normal curve is bell-shaped because it looks kind of like a bell. It's bell-shaped and it's got four important properties. The first of these properties is that a bell curve is smooth and symmetric. It's a curve. It doesn't come to a point. It's not the shape of an absolute value function. Again, it's a smooth bell-shaped curve. The highest point of our curve occurs over the mean, and we've got a little new notation here. We're going to see the mean represented with this symbol here. It's a Greek letter. So when we see this, that's the mean, and that's the highest point of our bell curve. The mean of the population is in the middle, the highest point of our bell curve. Our bell curve levels out as it approaches the x-axis. It never touches the x-axis, but it gets really close. And then the total area under our curve is always 1. The other special property that we get for normal curves, in addition to these, is how our data is split among a normal distribution. Okay, so right on either side of our mean, these are, as you can see at the bottom, labeled by standard deviations. So here's our mean. This is 1 standard deviation above. This is 2 standard deviations above, 3 standard deviations above. And then the -1 means 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. For a normally distributed data set, 34% of our data lies between the mean and whatever value is 1 standard deviation above the mean. So 34% of our data is in this chunk of our curve. 34% of our data is also between 1 standard deviation below and the mean. Remember that our curve is symmetric. So however much data I have in this section, I have the same amount in this section. Between 1 and 2 standard deviations, we've got 13.5% of our data, which means between -2 and -1 standard deviations, we also have 13.5% of our data. Between 2 and 3 standard deviations, we've got about 2.5%. So between -2 and -3, we again have about 2.5% of our data. Now it's very unusual to find data outside of 2 standard deviations. So the overwhelming majority of our data should be within 2. Outside of 2 is where we start to talk about outliers, but it is possible to have data outside of there, but it's a very teeny tiny amount that we would expect to see. It is possible, again, to have values that lie outside of 3 standard deviations or even outside of 4 standard deviations, but that would be so far from the mean, so far off of what we would expect or what we would consider typical, that we won't consider those cases for our purposes. So I'm just going to make a little note here that for practical purposes, we say that approximately 100% of our data is within 3 standard deviations of the mean. We won't consider anything outside of 3 standard deviations. And again, anything outside of 2 standard deviations is rare. Okay. A distribution that follows this pattern is what we call a normal distribution. This would be a normally distributed set. So why do we care about normal distributions? Why would we spend time talking about them? what we find is that a lot of real life data tends to follow a normal distribution. And we'll see that with several of the examples that we look at throughout this section. Height is something that's normally distributed. Most people are close to the average height for their age or their gender. And it's possible to have people who are a few inches taller or a few inches shorter, but it's rare to have somebody who's a foot taller than average or a foot taller or if it's shorter than average, I should say. Height is normally distributed. So are things like shoe size. So are things that we see in nature. Populations outside of human beings follow, again, normally distributed models. If I'm looking at weights of elephants, I would expect most of those elephants to weigh close to average. I wouldn't expect all of them to be exactly average, but I would expect most of them to be close. So most of my elephants would be in here. I might have some really big elephants. I might have some really small elephants, but that wouldn't be typical to have a huge range in the weights of those elephants. Most of them are going to be close to average. An example of a normally distributed set that you guys are going to have some experience with here before too long is the SAT. So the SAT is the results that we get are normative. It's a normally distributed set of results that we tend to get back. So on the SAT, you've got different tests that you're going to take. Let's say the mean verbal score for a given year was 425 and a standard deviation of 110. And then you have a math test that you're going to take. Let's say the mean math score was 475 with a standard deviation of 125. Now notice that the means are different here. They're different by about 50 points. Standard deviations are different too. Standard deviations a little higher for that math test. So let's take a look at what those curves would look like. So for our verbal score, I'm going to draw a little standard deviation here. Okay. Remember, the mean goes in the middle, and the mean for our verbal score was 425. So the average for all the scores for everybody who took this test was 425, and our standard deviation was 110. So anytime that I draw a normal curve, I'm going to split it up into 3 pieces on either side, 1 standard deviation, 2, and then 3 above. And then same thing on the other side, 1, 2, and 3 below. And I'm going to label these based on what I know the standard deviation is for this set. So the standard deviation is 110. So I'm going to add 110 to label each of these. So this would be 535, 645, and then 755. And then I'm going to label below as well. So this time I'm going to subtract that standard deviation. Okay? So this would be 315, 205, and 95. Okay, these are where my scores fall. Okay, now we've got information on our math score as well. So I'm going to set up a little distribution for that too. Same idea. Doesn't have to be a perfect bell curve as long as we get the idea. I'm going to put my mean in the middle. The mean for our math score was 475. And then again, I'm going to split this into these 3 chunks. My standard deviation sections on either side should be roughly equally spaced. This space should be about the same as this, should be about the same as this. Remember, this amount of scores in here is the same for each of these chunks. So this is 110 points, this is 110 points, this is 110 points. They should be evenly spaced, or as evenly spaced as you can sketch them. And then our standard deviation for the math was 125. So this would be 600, 725, and 850. Now, when we go down below the mean, we would have 350, 225, and 100. Okay, so there are some curves that represent the data that I've got. Now, what we're going to take a look at is my score compared to my friend's score. So I scored a 536 on the verbal portion, and my friend scored a 600 on the math portion. I want to know, how do these compare? So we got different scores, but remember that the mean for these tests was different. They're different tests, so it's hard to be able to directly compare one score to another when I was testing different things. So what we're looking to compare is, how did I do in relation to everybody else who took the test? Okay, so my verbal score was 536. That would be, here's 535 right at that standard deviation line. So that would be right above there. So that's my 536 score. And then my friend scored a 600 on math. Well, that's right on the standard deviation line. So as I'm looking at comparing these scores, what I actually want to look at is how did I compare based on the mean and the standard deviations, okay? So my math score, my friend's math score, I should say, was right exactly at 1 standard deviation above. 1 standard deviation above the mean. But my score on the verbal test was actually just ahead of that 1 standard deviation. This score was more than 1 standard deviation above the mean. Since my verbal score was farther above the mean than my friend's math score, that means that my verbal score was actually better. If I'm looking at who scored better on their tests respectively, that would have to be my verbal score because I scored farther above the mean than my friend did on their math test. Okay, so the verbal score was better because it was farther above the mean than the math score. So if you had a history test and a science test on the same day, and the history test was pretty easy, most people got an A or a B on it, and you got an A minus, that's a good grade, but you scored about average. Most people got an A or a B, you got an A minus, you're right in there. If on your science test, that was a harder test, and the average score on that was a C, but you got a B on it, a B is a worse grade than an A minus if I'm just comparing the letters. But if that was a harder test and you did better than average, you did better on the science test. That's what we're looking at here, being able to compare things that are normally distributed. So let's take a look at some more examples of this. On the next page, on page 21, we've got a couple of normal distributions given to us. What we're looking at here is normal distribution A and then normally distributed set B. Okay, a couple different ways that we can describe these. Notice they have the same mean. The high point of both curves is right over the top of 0. So my first couple of questions here ask about the mean for A and the mean for B. Well, the mean for A is 0. I'm going to practice my notation here. The mean is 0 for A. The mean is also 0 for B, right? The highest point of curve B is right over the top of A. So we've got two sets that have the same mean. They're both normally distributed sets. They're shaped a little differently now. Notice that A is much narrower, B is much wider, okay? That's because they have different standard deviations. So remember, anytime that I have a normally distributed set, I've got the mean in the middle, and then 1, 2, 3 pieces that I look at on either side. And we count our third standard deviation as sort of the ends of our data. So for A, if I'm looking at the standard deviation for A, I should have my 3 chunks all squashed in here between 0 and 1, okay? So for A, my standard deviation is gonna be, let me see if I can sketch these 3 pieces in here, would be to fit all 3 pieces in between 0 and 1, okay? I've got 3 chunks that I'm fitting in there. So my whole half, my front half of my data for A goes from 0 to 1, but that has 3 standard deviations in there. So that means 1 standard deviation would be a third. If I look at B, it also is going to have the same 3 pieces, 3 standard deviation sort of chunks on either side. And I'll sketch on the lower side for B this time. But this time I go from 0 to 3 or 0 to -3. That still has 3 standard deviations in there. But when I split it up, 1, 2, 3, this time when I break that into 3 pieces, my standard deviation, the difference between each of these sections, is just 1. So my standard deviation for B is just 1. That's what I'm looking at here. What's the difference? What's the amount between the mean and one piece up, or the mean and one piece below? What's the difference between those values? Once I know the mean and the standard deviation, I can start to say things about how much data I would expect to be between certain values for my data set. So I want to know for E, what percent of values would I expect to lie between -3 and -1 in set B? So between -3 and -1 in set B, how much data would I expect to be in here? Every normally distributed set is going to follow this same breakdown, this same pattern, okay? Now, it may not be exactly perfect, but it's going to be close enough that we're just going to keep referring back to these percentages for today, okay? Anytime we talk about normally distributed sets, and I'm asking you how much data would you expect, or what percent of data would you expect to be between the mean and one standard deviation, or between 1 and 2 standard deviations below, we're always going to refer back to these percentages. So we're looking at between -1 and -3. Well, this piece here would be 13.5% of my data. And then this piece here would be 2.5% of my data. So I'm just going to add those up and I get 16%. Okay, so I would expect 16% of my data for B to live in that range between -3 and -1. For F, what percent of values would I expect to lie between 0 and 1 in A? So from 0 to 1 for set A, that's this whole front half of my data, right? That's my forward 3 standard deviations. Remember, our curve is symmetric. This is the whole front half of my data, so that would be 50%. I would expect 50% of the values to lie between 0 and 1 for set A. We're going to continue to use these same percentages, these same sketches and breakdowns for every normally distributed set that we look at. So we have one more example that we're going to take a look at today. The bottom of page 21, we're going to look at example 3. And this is going to talk about height, okay? So height is one of those factors that's normally distributed. Talked about that at the beginning of our lesson for today. So if I'm looking at, let's say, adult females, I would expect most adult females to be within a few inches of average height. Some people are going to be taller, some people are going to be shorter, but I would be shocked if anybody were 3 feet taller than average or 3 feet shorter than average. Okay, most people are going to be close to that mean. So our data here is based on the heights of 1,000 girls. They're measured and found to be normally distributed with a mean of 64 inches, that's 5'4", and a standard deviation of 2 inches. It says girls, so I'm not quite sure what the age range is here, but for any given age range, I would expect if I took heights for 1,000 girls or 1,000 boys, or even if I looked at the population as a whole, just 1,000 kids, I would expect those values to be roughly normally distributed. So let's go ahead and sketch our curve here. Okay, my mean is 64, squeeze that in there. And then I'm gonna split my curve into 3 on either side. I know my curve always goes a little farther, but we count 3 standard deviations as about the end of our data. Remember, anything outside of that, we would consider an outlier. Okay, and then it says my standard deviation is 2. So I'm going to add 2, that'd be 66, add 2, 68, add 2, 70, and then I'm going to subtract 2. So 62, 60, 58. How many of the girls are over 68 inches tall? Over 68 inches tall. So that would be this chunk here between 68 and 70. We know, again, I'm referring back to my curve here, between 2 and 3 standard deviations, I expect 2.5% of my data to fall there. So 2.5% of my girls should be over 68 inches tall. Those would be my tallest girls. I know that I have 1,000 girls that I measured. So I would expect 2.5% of them to be over 68 inches tall. So I'm going to take 1,000 and multiply by 0.025, and that would give me 25 girls. Of my 1,000, I would expect 25 of them to be over 68 inches tall. Part C, how many would I expect to be between 60 and 64 inches tall? So 60 is here, and then 64 is my mean. So 1 and 2 standard deviations below. This would be 13.5% for this chunk here, plus 34% for this chunk here, 1 standard deviation below. So that would give me a combined 47.5%. I would expect to be between here and here. So since I know I measured 1,000 girls, I'm going to find 47.5% of 1,000, and that gives me 475 girls that I would expect to be between 60 and 64 inches tall. So almost half of my 1,000 should be 2 standard deviations below the mean, 1 to 2 standard deviations below the mean. That should make sense because that's almost the whole bottom half of my curve, almost the whole bottom half of my data. D, about how many are between 62 and 66 inches tall. So 62 is here, 66 is here. I'm looking at on either side, okay? 1 standard deviation below, 1 standard deviation above, within 1 standard deviation. This is, again, kind of similar to the margin of error problem that we looked at towards the beginning of our unit. So I know that this chunk is 34% and this chunk is 34%. So I'm looking at 68% of my girls should be between 62 and 66 inches tall. So if I had 1,000 girls, find 68% of them. That would be 680. Okay. More than half are within 1 standard deviation of the mean. That's what I expect for a normally distributed set. Okay. And then if I looked, we don't for this one, or actually we do, that's our next one. What's the probability that a randomly selected girl will be between 60 and 68 inches tall? So this is within 2 standard deviations of our data. This was within 1 standard deviation, right? 1 standard deviation on either side. This is going to take us to 2 standard deviations on either side. So I know this section is 13.5. And then this section is 34. This section is also 34. And then my last section here is another 13.5. Remember, it's symmetric. So when I add this up, I get 95%. Okay. Something important about normally distributed sets. I expect over half of my data to be within 1 standard deviation. Specifically 68%, but well over half to be within 1 standard deviation. I expect 95% of my data to be within 2 standard deviations. Okay, so unusual to get anything beyond 2 standard deviations, since that's 95% of my data. Okay, that's why we don't even worry about anything beyond 3 standard deviations for a normally distributed set. Okay, so what's the probability that a randomly selected girl will be between 60 and 68 inches tall? 95%. We gave probabilities as decimals earlier in this unit, so I'll go ahead and write that as 0.95. But that would be the probability I would expect one of my girls to be between 60 and 68 inches tall, to be within 2 standard deviations of that mean. Okay, so a couple things to remember. Our normally distributed curves are evenly spaced around the mean, and these other lines here are standard deviations that I'm going out from the mean. So 1 above, 1 below, 2 above, 2 below. Okay, I expect more than half, well over half of my data to be within 1 standard deviation of the mean, almost all of it to be within 2. And I can use those percentages from page 20 when I'm looking for the percent of values I would expect to be between any 2 given standard deviations.